Alright, so we are going through DMVPN, which is nothing but dynamic multi-point VPN. So we have covered the theoretical part yesterday, okay, and we are gonna cover the lab today. So basically we are gonna do the basic DMVPN configuration, and then we are gonna uh, check the phase 1. Okay, so under phase 1 we can have multiple routing protocols which DMVPN support. So we'll see once with EIGRP, we will check it out with OSPF and BGP. Okay, similar way we will also go ahead with phase 2. We'll do the same thing, and same thing with phase 3. Okay, but before that, let me just quickly recap what is DMVPN. Okay, so what is IPsec tunnel? It's site to site VPN tunnel which make use of public IPs. It has limitations. Okay, limitations of connections. We can connect 2 point to point connection. We cannot have 3 branch office or 4 branch office. The problem with the GRE tunnel, which is also widely used once upon a time, the header for GRE is very large when compared with the data, okay, or when compared with IPsec. So I can say that the data header, the header of GRE is gonna take lot of space. So the space for data is reduced. Okay, and also this is point to point connection. Okay, it's a point to point connection. Now regarding DMVPN, let's say if I have headquarter which is connected to internet connects to branch office 1 and branch office 2. Okay, so let's assume we have as usual the public IPs. Since this is a ISP, the service provider, so we have the public IP, let's say 1.1.1, 1.1.1.2 and 1.1.3 is the public IP. Now over on DMVPN, what I do is I set up a multi-GRE tunnel. Okay, so we make use of multi-GRE tunnel in the case of DMVPN. So we will lay this overlay connection. Now this green in color is nothing but it act as a overlay. Okay, and this overlay will be a private network, 192.168, any such network, whereas the red or the pink color, okay, it act as a underlay. It's basically the public IP which connects to ISP. Okay, so this is how the overview of DMVPN would look like. So DMVPN make use of multi GRE tunnels to form a server client relation. Okay, so you have a server which connects to multiple client. We also call DMVPN as hub and spoke. So this is my spoke 1, spoke 2, this is my hub. Okay, now what would be the scenario if I would have preferred the normal GRE tunnel? Okay, so if I have a normal GRE tunnel, it would have been basically a point to point connection between all of them. Okay, so you can see here I have 3 devices or 3 campus. I have 3 point to point GRE tunnel. Okay, So basically, the normal GRE tunnel is not advisable because of the number of GRE tunnel that we need to create. That's why we go with DMVPN. In the DMVPN, we just create one instance of VPN. Okay, so we just have one instance of VPN which will be distributed to number of spoke 2, spoke 1. I can also keep another spoke 3. So that's a benefit of the DMVPN. Now if you might be wondering, so the normal scenario is 3 spokes form a registered pair with respective to hub. Okay, something like your DR and DR others, or BDR in the case of OSPF, right? So each and every information you would be sending it to your DR. Similar way, in the case of DMVPN, the hub and spoke, the spokes will be in touch with hub. Okay. Now you might be wondering that if this campus which is in India, okay, if this campus wants to communicate with another campus which is in, might be Australia, do you think the traffic must go to the hub which is in US every time and then come to the Australia, right? So we have some option where the traffic can be directly sent between India to Australia. We don't have to send it to the US hub and waste lot of bandwidth. Okay, so that's why it's more popular nowadays in enterprise when you have your branches and headquarters. So the two branches can also communicate to each other despite of engaging hub for every single connection or a packet flow. Okay, so as we were talking about the DMVPN, so DMVPN has some components. Okay, the first component is MGRE, multipath GRE. Then we have NHRP, next hop resolution protocol. Okay, then we have those 3 phases: phase 1, phase 2, phase 3. And then we have the support from IPsec, because DMVPN don't have any encapsulation method. So we usually use IPsec layer with DMVPN. So these are few things which are the components of DMVPN. Okay, so what is MGRE? MGRE is nothing but, as a hub can connect to multiple spoke number 1, it can connect to spoke number 2, it can connect to spoke number 3. So basically I'm going to configure over here that this is a MGRE. Fine. So I can understand what is MGRE, but the problem with MGRE is, let's say if a switch 1, if a spoke 1 wanted to communicate with spoke 2. Okay, so basically what happens is, first the packet will be sent to the hub. Now as soon as the packet receives on the hub side, hub doesn't know who is that person that the spoke 1 is trying to communicate. Is it over to this, or is it over to this? Because the header of the packet would something look like this. Say for example, let's say the source, okay, the source of this would be, let's say this is 2.2.2.2, 2.2.2.2. Okay, the destination is not known, so I'm not sure what is the destination IP of this. Okay, what about the header? So it's a GRE header now. Okay, what about the underlay source and address? So source and address of the underlay. So let's say underlay is made up of on 192.168.1.1 and 192.168.1.2. Okay, so this becomes 1.2 and 1.1, and then you have your data packet. Now the problem is, once this packet is arrived on this, the hub doesn't know who is the destination. The destination could be either this or it could be either this, right? So to resolve this kind of issue, to know who is my next hop destination, we prefer this protocol, NHRP. Basically, this is a protocol which was launched in 1990s on the non-broadcast multi-access network. So this is a network type which was used widely in ATM X.25 technologies. Okay, but you know that NBA is obsolete in the market, but that protocol is used in DMVPN now. Okay, so what is the job of NHRP? NHRP will maintain a server, so this act as a server and these act as a client. Okay, now what happens is, as soon as we configure VPN, these spokes have to register themselves. That is the step number one from the client point of view. They will send a packet called as registered request. Okay, now what is that packet going to contain? It's nothing but it's gonna contain the public IP of their interface. So this is gonna say that I am gonna make use of 1.2, that's my public IP, 1.3 is my public IP, 1.4 is my public IP. And now what hub does is, hub is gonna make a dedicated table for NHRP cache, and this cache is nothing but it's your private to your public binding. What is private to public? I told you we have two things here. One is underlay and the overlay. Okay, underlay is that public IP which is used for ISP. Overlay is the tunnel interface which we are using for the DMVPN tunnel. Okay, so this public IP will be mapped to this private, and that entry will be collectively made up of here in this. So this is for the spoke 1, spoke 2 and spoke 3. Now whenever this packet from spoke 1 arrives to the hub, with the help of NHRP, we have this table ready. We are gonna see, okay, so 2.2.2 is fine, destination is question mark, right? So what is the destination over here? It's 1.1.1, let's say. Now what is 1.1? So let's say 1.1.1 is associated with 1.2. Okay, and there is how the hub gets to know from its NHRP cache table that the traffic is meant for this, not to this. Okay, so this is how the traffic flow happen in the case of DMVPN, and that's how the NHRP is going to help. Now we are good with DMVPN. We know how the DMVPN would be configured. Okay, now we will talk about the network that we are gonna advertise on these DMVPN network. Okay, so far the step number 1 and step number 2, we have achieved the DMVPN. If I do show DMVPN, I can see that I have two up and running DMVPN neighbors. But what is my traffic now? My interesting traffic. So let's say I have 1.1.1.1 and over here I have 2.2.2.2. Okay, let's take it as a LAN traffic which we need to advertise so that users over here can make use of DMVPN to reach to the other end. Okay, similar way, let's say this is 3.3.3. now this needs routing. Okay, the prerequisite of DMVPN is, if this user wants to communicate to this, they must be reachable via routing. Okay, so let's say if the traffic enters the DMVPN, it comes to the hub is gonna check the routing table and it's gonna forward it to the next person or the next hop. Okay, now to simplify the whole process, we have created 3 phases for DMVPN. Okay, the first phase is something when spoke 1 wants to communicate with spoke 2. So the traffic will be sent to the hub will check the traffic I mean to say, it will check its routing table, and then the traffic will be sent to the spoke 2. Now you might be wondering, in this scenario all the traffic are sent to hub. Is there any solution for that? Yes, we have some solution which will be used up in the phase number 2. So in the case of phase number 2, let's say spoke 1 is gonna send, so basically what happens is they first go via registered request, right? So basically they all get registered. So the step number 2 here is they are gonna send something called as NHRP resolution request. This is step number 2 in the phase 2, and for this you get something called as NHRP resolution reply. Okay, so what happens here is, let's say if the spoke 1 sends the traffic to spoke 2, okay, and now the spoke 2 says that this is the public IP of the spoke 2. Now they form a GRE tunnel between them. Okay, the GRE tunnel is going to get formed. Now what happens is the traffic will be sent directly from this branch to the second branch. It will not go to the hub. Only the first packet went towards the hub, where the hub gave the resolution of private to public. It said that this is what is the destination IP, and then it is sending it directly over the GRE tunnel. They are gonna be sent over the GRE tunnel. Now what about the phase 3 then? Okay, phase 3 also does the same thing. It's about eliminating the usage of a hub and just interacting between spoke 1 and spoke 2. But in the case of phase 2, we are gonna have the routing table, right? Because we are gonna have the routing table, and then whenever the spoke 1 is sending a request, a resolution request, it's gonna check its routing table. So basically the routing table of hub is getting piled up, lot of routing tables. So in the phase 2, we are going to minimize that. How are we going to minimize? There are two concepts now. So hub will make use of something called as NHRP redirect, and spokes are going to make use of something called as NHRP shortcut. Now in this phase 3, let's say spoke 1 wants to communicate with spoke 2. So as usual, it has sent this traffic, packet traffic with that question mark. Now what hub does is, hub will see that this is meant for another network or another spoke. What is hub going to do? It's not going to give the IP. Instead, it's going to reply back with the routing table information. So the routing information will be sent to the spoke 1 and as well as spoke 2. Now they both have their routing information to reach the second spoke. Okay, second thing what we see in phase 2 is we can also make use of a summarized routing table so that we can reduce the number of lines. This doesn't work in the case of phase 2, because in the phase 2 the routing should be mandatory required. If there is no routing, if there is a missing routing, the spoke 1 will not know how to reach the spoke 2. You cannot minimize this. Minimize is nothing but, if I have 1.1.1.0/24, if I have 2. Let's say 1.2.1.3.16 something. So we just summarize like this, right? So this summarization is not possible in phase 2, but it is possible in phase 3. Okay, and in phase 3 we don't need the routing tables. So as soon as it's going to detect that the request is for the another spoke, it's going to reply back with the redirect, and the spoke 1 will now directly communicate with the spoke 2. Okay, so we were left out with the lab. So let me quickly move on to the lab part. Okay, so I have these three routers. I'm making use of these IPs. So I have my underlay. Underlay is nothing but that public IP which connects to ISP. I have overlay which is used for my tunnel creation, which is a private IP. And then I have the local area network, something like this. Okay. So I have 2.2.2 series. I have 3.3.3 series. This is just a ISP cloud. Just I have placed L2 switch. It's nothing. It's not doing any work here. It's just a broadcast type of device. Okay. So this is the setup. We will see how the DMVPNs are established. We will enable the routing like EIGRP routing, OSPF, BGP, and we will see how the trace route work. If the traffic has to go this way, or if the traffic can go directly this way. So that is something which we have to check. Okay. So we need the console. And yes, the reason why I took this EVNG is my GNS is corrupt. Okay, I'm not able to load that. It's getting failed. So that's the reason I took this. So don't be confused with this, because we have this kind of the topology in our GNS itself. So if I have to show you, this was the part which we created for DMVPN. Okay, so you can still practice on the GNS itself, but for me my GNS is not working after the latest upgrade, so that's why I'm stuck with this kind of small lab. Okay, so let's configure this. The DMVPN lab configuration is too lengthy. It's going to take a lot of time. You might lose your interest now in the live class, but I suggest after the class go back to the video and try to do this. Okay, then only you will understand uh, the commands and the flow about this. Okay, so let's start with the first configuration. The first configuration is for the hub. Okay, and I have the configuration with me. Okay, this configuration will be also put up in the notes, so don't worry about that. Okay, so I'll just walk through about the first few commands. Okay, so first let's go and configure the host name so that we know what is which device here. Fine. So what is my interface here? It's FA0/0. Let's give an IP address of so what is my underlay? Underlay is 10.1.98.255.255.255.250. No shutdown. Okay, this is my, as usual, the interface IP here. That's nothing but the underlay. Okay, so once I've done that, let's configure the tunnel interface. So under the tunnel interface, let's configure its IP address. So we are going with the private IP 172.168.1.98.255.255.250. Okay, no shut. What tunnel mode is this? If I do a question mark, so this is a GRE multi-point. Okay, the GMRE which we the MGRE which we discussed. Okay, what is a tunnel source here? So tunnel source here is fast Ethernet 0/0, the physical interface. Okay, what is the authentication? It's better we secure our packet. So let's say the password is this DMVPN, and let's map this interface IP NHRP with the multicast. Okay, so the reason why we do this is basically I'm gonna tell that this hub or this router will also support forwarding multicast packet. So why do I need multicast packet? Basically what happens is when this spokes try to register later on with the with the hub, they will follow the multicast packet. Okay, so I'm giving the provision now itself on my interface saying that I wanna map my hub interface so that it recognize the multicast traffic. Okay, so basically the command tells the hub router where to forward the multicast packet to. Okay, the IP address of the spoke router would be unknown. I told you the IP address would be unknown, so it has to be reaching to the hub, right? So basically, we just assign a multicast IP on that destination, this destination. So any packet which is not having the destination IP will be sent on the multicast listening IP address. Okay, and there is where the hub will then reply back and they will know their public IP. So this is a configuration from the tunnel side of view. So let's come out of this. Let me copy this, or I have this already, so I can show you here. So I configured my interface, I configured my tunnel. Okay, so I said the mode GRE, source, FA0, authentication, multicast, and network ID. Network ID is when you have two or more networks. Okay, so when you have two or more network, it will be difficult for you to troubleshoot. So you are setting up this ID stating that this is your first network. So when you have your second network, you are gonna do that. So I think I have missed that command. So let's place that. IP NHRP okay, 1 second. Fine, so this was the hub configuration. Let's go to the spoke now, the first branch office. So the spoke configuration will be the same on both the spoke side. Okay, okay, let's make it as spoke 2. Let's go to its interface. Let's say it's 10.1.9 255.255.255.0, no shutdown. Let's also go to the tunnel interface and let's say this has the IP address of 172.168.1.99.255.255.255.0. Okay, tunnel is that private IP range. And then I'm gonna set the authentication DMVPN. I'm gonna map my private to public. I'm gonna say IP NHRP map 172.168.1.98. Okay, and if I do a question mark, what is my NBA address now? So the NBA public address would be 10.10.1.98. Okay, so that's nothing but from the spoke point of view, I'm giving the private and public IP of my hub. So this is my hub private IP and this is my hub public IP. So I'm mapping them. What else? We have to define or we have to map the multicast traffic towards this public IP. So I say IP NHRP map multicast to 10.10.1.98. Okay, I'm gonna set the network ID also, where I say IP NHRP network ID 1. And who is my next hop server? Who is my hub? I'm gonna say IP NHP next hop server or my hub is this guy again. Okay, sorry. So this is my next hop server. So Spoke is assigning this as a next hop server. Okay. What is the tunnel source here? Tunnel source is F0/0 and tunnel destination is 10.10.1.98. So configuration from the first Spoke point of view. If I want to check if my DMVPN status, we can check that. Show DMVPN. Okay, they don't seems to be up. Let's see. So this is up. Okay, the physical interface is up, and also this is up. So let's wait for some time. Okay, interface is up. .10.1 network ID. Okay, let me try by flapping the interface F0/0 shut down. No shut. Show IP int brief. Okay, so these are up. That's a good thing. I hope I have not done the IP address mismatch. 99.10.1. Okay. Show run interface tunnel.0. Let's quickly ping the tunnel. So this is spoke 1. Okay, so the issue is Okay, that's fine. So that's 1.99. Okay, fine. 1.99, 1.98 to 1.98. Fine. And okay, the mistake is here. Okay, so the next hop server is that overlay IP address. Okay, not the underlay IP address. So there's a typo in the this particular line. So I'll take this out because I'm referring to my NHRP or the DMVPN IP. So DMVPN IP is on that 172 series. 10 is your ISP IP. Doesn't make sense that we have that. So I'm going to put this as 172, 168, 1.98. Okay, let's press enter. And there we go. We have our first DMVPN neighbor. Okay, this is on DMVPN. This is my first spoke. This is the DMVPN tunnel address. Okay, what is my NHRP or the next hop router? So this is my DMVPN spoke 1. How do I travel? I travel via this next hop. Okay, and this is my NBAMA address 10.10.1.9. Now let's bring up the second spoke. I'll copy this, or I have it already here. Okay, now let's configure the same thing on the next hop. So I just have to change the IP address. This will go towards my spoke 2. Let's also configure the interface, physical interface, IP address 10.10.1.100 255.255.255.0. No shut. Okay, let's see if the DMVPN takes it up. Okay, and there we go. We have two spoke connected as neighbor, or I can say the hub is having the neighborship, DMVPN neighborship with two spokes. Okay, show IP NHRP. So it's good so far. So whatever we did is that we only build the DMVPN. We have not tested the packet now. We have not advertised the local area network now. Okay, so we shall do that now. So let's go to conf t. So on the hub, I'm going to create a loopback, and I'm gonna say it's 1.1.1.1 255.255.255.0. Okay, now these are going to be your phase example for your phase demonstration. Okay, so so far what we did, so we did the DM VPN basic configuration. Okay, now we are gonna check those phase 1, phase 2, phase 3, and I told you each phase, I guess some problem with the pointer. Yeah, so each phase 1, this is still worst. So each phase we can check it out with the routing protocol like EIGRP, BGP or OSPF. Okay, so let's see the first with EIGRP. So I just configured some loopback and we are gonna enable EIGRP and we are gonna advertise it. So let's say 1.1.0 and let's give some wildcard mask /24. Let's also advertise 172, that is the overlay or the DMVPN IP address 172.168.1.0.0.0.255. Okay, and no auto summary. We are just disabling the auto summary. Same way, let's go to spoke 1. Let's go with EIGRP1. Let's say let's define or let's advertise the network 2 dot, which is going to be the loopback, which I'll create now. Okay, and the second network is 172.168.1.0.0.0.255. Okay, we have not created the loopback. Let's create loopback IP address 2.2.2.255.255.255.0, no shut. Okay, so there should be one adjacency by now. Show IP EIGRP neighbors. Okay, so we have one adjacency with 1.99. Similar way, I'll go to my second spoke and I'll do the same thing. Let's configure the loopback IP address 3.3.3 255.255.255.0, no shut. Let's go to router EIGRP 1. What is the network you wanna advertise? So we have the overlay or the DMVPN IP. That's the first thing. And second thing is our local area network, which is 3.3.0 and class 24. And finally, no auto summary. Okay, I can also do no auto summary here. Fine. Let's see the EIGRP tables. Okay, so we are good. We have two neighbors. Now time to test it. Okay, time to test the traffic. But before that, let's first validate the neighborship and routing information from all the three of this hub, spoke 1 and spoke 2. So if I want to see the routing table, I am good with 2 and 3 from my hub point of view. Okay, so from hub point of view, I'm good with this and this. But what about from the spoke point of view? Can I see this and can I see this other network? Similar way, from spoke 2 point of view, can I see this and can I see this network, the spoke 2? Let's check it out. So let's say show IP route EIGRP. So I can only see 1.1.1. Okay, I can only see this, but I do not see anything beyond that. Now similar way, if I go with my spoke 2, can I see the spoke 1 network? Show IP router EIGRP. No, I don't see it. I can only see till my hub. Now the issue here is split horizon. Okay, so you know that EIGRP supports split horizon. Okay, so in order to avoid looping, what split horizon does is split horizon will cut down the advertisement of this network. So from the router 1 point of view, only this network will be visible. Okay, not this. So let's put that split horizon off. So let's first close that behavior. So let's go to the hub. Okay, and let's disable that. I'll go to my interface tunnel and I'll say no split no IP horizon EIGRP 1. Okay. So the moment I do, the neighbors have updated. Okay, the update packet has updated the features. So now let's see what is the new route, because if you see, prior to the split horizon, we could only see the one series. Now do I see the 3 dot series? So yes, I can see the 3 dot series. What about from the spoke 2 point of view, which was able to see just 1.1? Now the spoke 2 can see the 2.2 series, which is nothing but the LAN for spoke 1, right? So if I redo the same command, so yes, I can see the 2 routes. So basically I should be able to ping, right? So let's try to ping to 3.3.3 on my source loopback 0. It's reachable. Okay, so my traffic over VPN is flowing properly, but I am not sure if this traffic is flowing every time over on the hub, or my hub has taken care and the traffic is directly flowing between the two spokes. I'm not sure, right? So to make sure about that, I can quickly do a trace route check. So let's say trace route, and let's check 3.3.3. Okay, so let's see how this thing work. So it went to 98. So who is 98? 98 is my hub. This person is 98. So that proves for phase 1, the traffic will be sent to 98, and the 98, which keeps the lengthy or the bulkier routing table, will check its routing table and then finally will send to spoke 2. Two things here. One is your routing table is just getting expanded, and second thing is every packet will be sent to the hub, and then hub will make the decision. Okay, this is phase 1 with EIGRP protocol. Now the same phase 1, let's see from OSPF point of view. Okay, let me delete the EIGRP as of now. We are gonna keep the same basic DMVPN configuration. We are not gonna remove that part, the tunnel part. We are not going to remove that. Let's configure OSPF. So let's say router OSPF 1. What are the networks that I wanna advertise? I wanna advertise 172.168.1.0. What is my wildcard mask? What is the area? 0. Okay. What is my local area network? Okay, the same way I'll go and do it on spoke 1, network 172.168.1.0.0.255 area 0, network 2.2.0.0.255 area 0. Okay, so we can see one of the neighborship has already come up. Okay, and they are forming the full status. Okay, similar way, let's enable the OSPF on spoke 2, network 172.168.1.0.0.0.255 area 0, network 3.3.0.0.0.255 area 0. Okay, let's see the OSPF neighborship. So it's in the exchange state, but what is that in the backend that we see is happening? So in the backend, we see there is lot of flapping happening. Okay, OSPF is resetting its neighborship with 2.2.2 and 3.3.3. Okay, See, you can see the neighborship is getting broken up or fluctuating. See, it's going to init, extract, exchange, and back to init. Okay. Why do you think this is happening? The reason is the moment I configured the OSPF on tunnel interface, okay, by default tunnel interface works on point to point. Okay, that's the default behavior of tunnel, point to point. But over on my hub I have configured MGRE. So basically what MGRE is going to do, it's going to build the DMVPN on both the destination. But what is the theory behind point to point? Point to point is direct connection, right? So this should be the one connection, not two. So from the hub side it's going to make two connection, but from the spoke side it is trying to negotiate at one single connection. Due to this we see there's lot many fluctuation happening, there's lot of flaps happening which is on the hub. Now what I'm going to do is, the simple option would be just change the network type to broadcast, so that they form the DR BDR connection. It would look like a multi-access network now. Okay, so there will be a DR BDR election, as we know in the case of the multi-access network. Okay, so what I'm going to do is I'm going to change the tunnel to broadcast OSPF type. The moment I do that, this will be taken care. But there is one more scenario that might arise, that is, what if the DR is being taken by this guy now? Okay, I want the DR to be this person because he is my hub. I don't want the DR to be either this spoke or this spoke. Okay, so to do that, I'm gonna disable the DR negotiation by setting priority to be 0. So you know that the moment I set the OSPF priority of these two routers 0, they will not participate on DR BDR election. So I have this as DR always, and these are as DR others. Okay, so let's do that. So first let's make use of a notepad because I have to copy paste immediately. So I say this tunnel 0, it's a OSPF network broadcast type. I wanna make sure my DR is always this, right? So this is a hub configuration. Okay, over on hub, over on spoke, and also on spoke 2. Okay, but from spoke 1 and spoke 2 point of view, I'm also gonna take them out from DR BDR election. I'm gonna set IP OSPF priority 0. Once I do that, I have to make sure that I clear the process. Okay, let's copy this and put in the hub. Okay, so we did that. Let's go to the second router, which is spoke 1 and then spoke 3. Okay, fine. So the neighborship went down and they are coming up. So let's wait for that. And meanwhile, I'll also remove the priority so that they don't get elected as a DR. Fine. Once I've done that, let's straight away clear show IP OSPF neighbor. So I can see the things are coming up. They are negotiating the 7th state of OSPF. So this is the two-way state. It will go to extract, exchange, and all the other things. Okay. So you can see hub is taken as DR. Okay, fine. So they have gone to full state. Now what do you understand by this? Your spoke are now DR other. Okay, your spoke 2.2 and 3.3 is always DR other. We don't need them to be DR or BDR. Whereas your hub is always DR. So this is when you have DMVPN phase 1 with OSPF. In OSPF, we will not be worried about split horizon. So we should be good to test it immediately. Okay. So let's go to my second spoke. Let's first ping the spoke number 1. Let's say loop back 1 or loop back 0. It's reachable. Let's see the trace route of this packet flow, and then we can conclude what happens in phase 1. So I'm expecting it goes via this over on OSPF routing protocol. So let's verify. Okay, so it went to 98 hub, and from hub it will pass on to the spoke 1. So that proves that phase 1 is always dependent on hub. Hub will have all the routing information. So this is something is mandatory in phase 1. Okay, let me quickly also show the BGP. So let's first remove OSPF configurations. Okay, let's go to hub, and let's say it's a autonomous system of 65,000. Who are my neighbors here? So from my hub point of view, my neighbors are 172, 168, 1.99, which is spoke 1, and let's say the remote AS is 65,002. Okay, and the second spoke IP address is this, and its remote AS is this. Okay, so from hub point of view, I configure two BGP neighbors. So I say this BGP neighbor is 65002. Okay, and then over here I say 65003. Dot 99 and dot 100, dot 99 and dot 100. So this is my BGP configuration on the first box. So similar way, let's go to the spoke 1. Let's say BGP. Now this is 65,002. Okay, I have not advertised my network here, so let's also do that. Network 1.1.1 mask 255.255.255. Or let's make it as class C. Okay, let's go here. Let's say 2.2.2.02 mask 255.255.255.0. So for my spoke, it's only one neighbor who that's my hub. So it's 65,000. So similar way, I'll go to my spoke 2 and I say BGP 6503. Which network is this? 3.0 mask of 255.255.255.0. Who is my neighbor? It's my hub 172, 168, 1.98, remote AS of 65,000. Okay, let's verify the BGP neighbors. To show IP BGP summary, I can see the two neighbors. Okay, but one shows to be never, but let's wait. Okay, it has come up now. Okay, so I can see them to be good and working. let's give a ping test immediately. Let's ping the spoke 2 from spoke 2 to spoke 1. So let's say spoke 2.2.2 source loopback 0. It's reachable. But what is my traffic? So as we know, in case of phase 1, the traffic should be over hub always. Okay. So there you go. You can see it went to 98. 98 is nothing but the hub, and from hub it's going to the spoke 1. So this was the traffic flow. Okay, and this is the case in phase 1 where you see a lot of routing tables and all the routing should be learned. Now this is not a good approach. So what I'm going to do is I'm going to move to the phase 2 of DMVPN. So to do that, let's reload this router so that I get a fresh copy of router and I redo this configuration. Otherwise I might mess up from my phase 1 config, because there are some changes which I have to do it in the basic DMVPN configuration. So let's stop them first. Let's start them. Let's take the console. So what is the benefit of DMVPN phase 2? So there are two changes when compared with the phase 1. The first change is now the spokes are also gonna make use of MGRE. Okay, in my phase 1 I had configured it as a point to point connection. If you remember, I said tunnel destination as 172.168 1.98. Now in the phase 2 this command would be taken down, and instead of that command we are gonna say IP NHRP mode MGRE under spoke 1 and spoke 2. So that's a major change in the case of phase 2. And there is one more changes, that is we don't need to configure the manual destination. Okay, there is no need of manual destination. If you remember in phase 1 we said that tunnel source, which is still required, but there was one more statement called as tunnel destination. We said that 10.1.1.98, right? So we don't need this now. So these are the two changes from the CLI point of view. Okay, and what is the benefit of this? The benefit is traffic will be talking directly between spoke 1 and spoke 2. Okay, the first packet will still go in this direction, spoke 1 to hub. Similar way, spoke 2 to hub. Okay, so basically we call this as registering. So they register their private tunnel IP to their public IP. And what is hub going to do? Hub is going to maintain the NHRP catch table. So the next, let's assume that spoke 1 wants to communicate to spoke 2. Now the traffic will go to spoke 1 from spoke 1 to hub. Okay, and that is resolution request. It's called as resolution request. What does that contain? It's nothing but it is going to ask what is the destination public IP. Okay, and hub is gonna reply back to SPOC 1, which is called as resolution reply, and now it's gonna say that destination is the destination of the SPOC 2 is 10.1. So basically it was 10.1.1.100, right? And then SPOC 1 will directly talk to SPOC 2. We can try that when I do the traceroute command. Okay, so this is a change between the phase 1 to phase 2, the benefit of phase 2, and also the changes from the CLI point of view. Okay, what are the different CLIs in the phase 2 configurations. Let's go to conf t. Let's say host name as hub. Let's configure the fast Ethernet. Let's say it's 10.1.1.98.255.255.255.0. No shut. Let's go to tunnel interface, and let's say it's IP address 172.168.1.98.255.255.255.0. It's hub, so the basically it's going to be GMRE, or we call it as MGRE. Okay, multi-point GRE mode. What is the source here? Source is F0/0. What is the authentication? DMVPN, and we are gonna say IP NHRP map dynamic or multicast dynamic. This is required because the traffic from SPOC, when they don't have the destination address, will be sent over on multicast. Okay, so you are just enabling this multicast listening on this tunnel interface. So this is for hub. The hub configuration is same. If you remember the phase 1 and phase 2, now the hub configuration, there wasn't any difference. Okay, but let's see the changes in the SPOC side now. So let's go to conf t. Host name SPOC 1. Okay, let's define the physical IP address 10.1.1.99.255.255.255.0. No shutdown. Interface tunnel 0, IP address 172.168.1.99.255.255.255.0. IP NHRP authentication DMVPN IP NHRP map 172.168.1.98 to 10.10.1.98. Okay, this is nothing but this is the hub private and public. IP NHRP map multicast to 10.10.1.98. okay, we have already enabled the multicast dynamic on hub, and we are now enabling the multicast on this side. So basically the spoke should know that this is listening, this interface. IP NHRP network ID as 1, IP NHRP the next hop server, which is my hub 172.168.1.98. who is my tunnel source is FA0/0. Now I'm not gonna go with this command anymore. Okay, this command is not applicable in phase 2. Let's make this instead as GRE, which was not done in phase 1. Okay, this is a new command which I'm going to do here. Okay, what are the command? So this is the command. I'll just copy this and I'll just put up in the notepad so that I can just change and copy paste. Okay, so this is my spoke 2 interface f0/0 IP address of 10.10.1.100.255.255.255.0 no shut. Okay, so this will be put in the second spoke. So let's say it's enable conf t and let's paste. Okay, so let's see what happens now. The basic DM VPN should come up. Okay, they have not come up, so might be I have missed something. Let's quickly check the configuration. Okay, looks like I have missed something. Okay, let's just check with Spock now. Okay, the network ID command is missed. Is that something else? This is a Spock command, not a hub command, but this is important command. Okay, so let's place this. Yeah, so we can see the things are coming up, but we have only one. Okay, both have come up. Okay, so the DM VPN is up. The DM VPN is up between the hub and the two spokes. Now, what about the traffic so that we can test and identify what is happening here? I've also taken up the Wireshark. So you can see as soon as the hub and the spokes were configured, there was a registration request sent, right? This was the request registration, the first step which I told you. Spock 1 is gonna send its private and public information to the hub, and similar way, so you can see the registration came from 99 to 98. This was Spock 1 to hub. Similar way we can also see for 90. Okay, we can also see for 100. This came from the Spock 2 to the hub. Let's try to see if we can see the content of it. So you can see here it's mapping all its required information. So 99 being its physical IP, 1.99 being its tunnel IP, and so basically these are the two IP which Spock 1 is telling to the hub. Whom is this to information sent? You can see source and source being informed to the destination. Okay, private and public of the Spock 1 is being informed to the hub, and hub is gonna create the table. So if I see NHRP, Okay, so what is this? This is SPOC 1. SPOC 1 is connected to this public IP. This is SPOC 2, which is connected to this. So basically this is acting as the catch table. If any packet which is coming over on NHRP, okay, which is meant for SPOC 2, what did we say? It's going to send back the information over on resolution. Okay, we don't have any resolution packet now, because SPOC 1 didn't try to communicate with SPOC 2 as of now, right? So we don't have any communication between SPOC 1 and SPOC 2. We will enable that by uh, configuring some routing protocol, EIGRP, OSPF or BGP, and then we can see what happens here. And then you will see that the resolution request and resolution reply packets have been generated. As of now, the first step is register request, okay, registration. Let's go to the configuration. Let's first start with EIGRP. Router EIGRP1. Let's define the networks that I'm gonna advertise. It's 1.series 0.0. Okay, 1 second. Yeah, fine. So let's give the wildcard mask. What is the next network that I want to advertise? 172.168 1.0 0.0.0.255. Okay, same commands, or at least the same type of commands will also be put up on the SPOC, where it says 2.2.0 0.0.255 network 172.168 1.0 0.0.0.255. okay, and on the third or the SPOC number 2, router EIGRP1 network of 3.3.0 0.0.0.255 network of 172.168 1.0 0.0.0.255. okay, let's see the adjacency now. Show IP EIGRP summary. So I have the neighborship with both the SPOCs now. What about ping command? Will the ping work? So let's ping 2.2. network, which is the loopback of my SPOC 1. So let's also give the loopback. Okay, I have not configured loopback, which is important. IP address 3.3.3 255 255 255 255. No shutdown. Same thing, let's do it over here. IP address 2.2.2 255 255 255 255. No shut. Interface loopback 0. IP address 1.1.1 255 255 255 255. No shutdown. Okay, so let's see the routing table first. Yes, we have the routing table now. Okay, what about the routing table on the SPOC ends? So we can see the first hop, but we don't see the second one. So we know it's a EIGRP and we have to turn off the split horizon. Otherwise, it will not let me to see the second hop, right? So let's go to router. Let's go to interface. It's an interface command. Let's say no split. Okay, no IP split horizon EIGRP1. Okay, now let's see if I can see two networks here, and there we go, we see two networks. Now interesting thing is to see what is the packet flow, whether it goes via hub or it goes straight one to one, right? So let's initiate a ping. When I initiate a ping, we will see that the resolution packet will start hitting here. So let's say 2.2.2 and source of loopback 0. Okay, so let's see what are those packets. So you have this ping packets between 3.3 and 2.2. Okay, but how do I confirm whether this is going via hub and not over on not is going over via directly via SPOC 2 and SPOC 1 and not hub. So let's do a trace route. Okay, now interestingly, if you see this, the things have not been resolved, right? We can still see this is passing to dot 98 and dot 98 passing to dot 99. Now this is not a behavior of phase 2, this is behavior of phase 1, but don't blame the phase 2 EIGR, don't blame phase 2 DMVPN for this. This issue is due to EIGRP protocol. Okay, now what is happening here is the next hop is not getting resolved. Okay, so basically what is happening here is when the SPOC 1 is trying to reach SPOC 2, it's still going through the hub, because EIGRP is not changing the next hop. That's a problem with EIGRP. If I make use of OSPF, it would have been taken care by OSPF, but EIGRP is not changing its behavior. So what I need to do is I need to turn off that feature. Okay, so I'll go to hub once again. We have taken care of split horizon. We can see the route, we can ping it, but the next hop has to be taken care. Okay, so let's go to interface tunnel now, and I say no IP next hop. Okay, no IP next hop self EIGRP 1. So basically I'm asking the EIGRP to take out the next hop self command. Okay, so now what happens is it will see the DMVPN phase 2 configuration irrespective of the next hop self. The next hop would have been sending to this. Okay, so let's redo the ping and redo the trace route. So from ping point of view, it's reachable. And do you see now we have the resolution packet? That means my SPOC 1, which is 100, is that it went to dot 98, dot 98 went to dot 99. We have the same thing happening between the other side also. The resolution reply and request has been taken care. Okay, so we can see it's reachable. What about the trace route? So let's see what the IP it resolves. It must give us dot 99. Okay, so it is giving us dot 99. That means, see, you can see just one hop. That means the traffic went directly here. Okay, it didn't go towards hub and hub didn't route it. It directly went between the SPOC 1 and SPOC 2. This is phase 2 of DMVPN, where you can achieve the DMVPN, you can set the IPsec encapsulation. Also, you can communicate between two branches. You don't have to depend always on the hub for this. Okay. So this is in the case of EIGRP. The same thing happens with OSPF also, and same thing with the BGP also. In case of OSPF, when you enable the default OSPF, you will see the fluctuation happening on the hub, because hub is configured on MGRE, multipath GRE, but point to point is expecting one neighbor, but hub is trying to make two neighbors, and due to which then the flap is happening. So we will not be we will not configure point to point. Okay, we can straight away go with the broadcast, and we can just fix that up. Okay, so I let that part for you guys. And BGP is also very similar what we did, because the main configuration lies on the DMVPN configuration, not in the routing protocol. Routing protocol is same which we are going to do on phase 1, phase 2 and phase 3. Okay, in case of EIGRP, I have to take care of my split horizon, next hop. OSPF, make sure it's not point to point, just broadcast is supported. Also non-broadcast is also supported, but point to point is not supported. Okay, BGP, eBGP is supported, iBGP is supported. Okay, with respective to phase 2 and phase 3, let me tell you what do we have in phase 3 now. Okay, so from the basic configuration, the basic DMVPN configuration, they are same. Okay, they are going to be very same. So let's say I have some configuration for my tunnel of DMVPN. Okay, I just have to add one or two lines here so that it migrate from phase 2 to phase 3 automatically. The command here is, I just want to go to tunnel 0 and I have to say IP NHRP redirect. You know what is redirect command going to do. When a request is coming from SPOC 1 towards SPOC 2, it's just gonna send the routing information to both SPOC 1 and SPOC 2, and it's going, and they are gonna and the hub is gonna tell that you both can communicate by yourself. You don't have to depend on me, and this information will be put up in the routing table of SPOC. So every time this packet will not be hitting the hub. Okay, that's one change, one benefit. The second benefit is, if you see the current routing table, you will see there are a lot of routing tables. Okay, you cannot summarize them, because the phase 2 relies on this routing table. If at the moment you summarize this to 0.0.0.0/0, the communication will break. That's the phase 2 says. But in the case of phase 3, you can summarize this, because when you're sending those uh, redirect, or when the in the case of phase 3, when SPOC 1 and SPOC 2 are sending those NHRP redirect command or redirect traffic to the hub is gonna send the information and it's going to close its interaction, right? So the routing table doesn't play very important role. So we can just place a default route itself in a zero dot series. Okay, and that makes this routing table reduce. We don't need a lot of lines. So these are the benefit of the phase 3. But the problem is, with respective to configuration, I cannot configure the required command here, okay, the NHRP redirect. See, this is what happens. So might be this particular OS, this iOS is not compatible for the phase 3 DMVPN. So this is a 72 series with this code, but this command doesn't take up, okay. So that's a catch where I cannot show you the phase 3, but yes, I can tell you the configuration that migrate from phase 2 to phase 3. So this is one command which is to be put up on the hub, which makes this from phase 2 to phase 3. On the Spock side, the migration is again is another command, but that will work, but I cannot test it because this is an important command on the hub, and that one command, if it would have worked, then we could have checked this, okay. So on the Spock side, I go to the tunnel interface, I go to IP NHRP, and there's something called a shortcut, okay. This has to be enabled. So the moment I enable this, the phase 2 DMVPN will migrate to phase 3, okay. So this command is a working command on a Spock, but the command for hub is not compatible with this iOS version, this lab iOS version, okay. Might be this will be compatible with some other high-end boxes. So on the Spock 2, if I go and do the same thing, tunnel 0 IP NHRP shortcut, okay, it's a working command, and rest is the same thing. You configure EIGRP, you advertise the network, you disable the split horizon, you disable the next hop gateway, and once you do that, initiate the ping and initiate the trace route, and you will be able to see the way the DMVPN works in the case of phase 3 is little different than the phase 2, okay. Also, you can summarize the route in case of reducing the number of lines, okay. So that ends the DMVPN concept. It's very lengthy concept. We took 2 days to complete this. In your syllabus, they have just mentioned configure and verify DMVPN, okay. So we discussed GRE, NHRP, IPsec, dynamic neighbors, and spoke to spoke, okay. So IPsec is something where you are giving that additional security to the DMVPN. It's always best practice or advised that when you're sending the DM packets over on internet, so let's say I have my hub connected to ISP connected to spoke 1 and spoke 2. Now the traffic or the packet which leads to internet, it's always advised that add the IPsec security, okay. So we can add the IPsec security here, and it's very similar the way we had discussed it earlier. So we have to create the ICKMP policies, and we have to create the IPsec policies, okay. So on hub Spock 1 and Spock 2, we should configure crypto ICKMP policy, okay. We have to define the hash tagging or whatever the authentication is pre-share. We have to enable the encryptions AES 128, the group, the Diffie-Hellman group, and the hash value of SHA-256, okay. And then we have to set some strings here, or the P key, the pre-shared key, the PS key. So crypto ICKMP key defines some key like DMVPN key. Address, what is the address here? So address is nothing but your NHRP address. So let's say 10.1.98 is your address. Okay, and then you will define the phase 2. So the phase 2 will be the transform set, which we know, crypto IPsec transform set, and we just define ESP, AES, ESP, HMAC. Okay, mode transport. So we know that there are two types of mode. One is called as tunnel mode and transport mode. Okay, so tunnel we used in the case of IPsec site to site. Now we are using transport for DMVPN. Okay, so this we can set it up. If you want to change it to tunnel, you can still make use of it. And then we set this under some profile. So we say that this is a part of crypto profile. Let's say it's a DMVPN profile. We then go to the tunnel interface, tunnel 0, and then we call this particular profile. So we say this tunnel protection IPsec profile DMVPN profile. So this is how your DMVPN traffic now gets associated with the IPsec protection or IPsec security. Okay, so this is not part of the CCNP portion, but I thought of including this. Okay, so well, that ends the DMVPN. Let me quickly take you guys to this syllabus copy. Let's mark this as completed. So pretty much done. We are left with this IPv6 and MPLS from NRC, and from NCore we have this 5.5. So multicast we did already, but we had not marked it. So we have this 5.5 series topic, 2.3, 1.6, 1.4, and this SSO I'll just cover up now. Okay, it's just a short topic which we can cover it now. It will take 5-10 minutes, that's all. So these are again all short kind of topic, might be 2-3 things I can combine. So might be next 2 days we can wind up the whole syllabus. Okay, SSO, it's called as stateful switchover. Okay, if you remember, if you just saw this was being added up with along with the HSRP, VRRP, or I can say the first hop redundancy protocol. Okay, so since it was added up with these protocol, I would say that this would provide us some kind of redundancy, right? Where is it going to provide us redundancy is now what, that's something which we are going to discuss. We know that these are in terms of the device failures, right? If I have, let's say, 2 router, I'm connecting it to a switch, I'm gonna enable the HSRP here. So let's say from my LAN user point of view who was sending the traffic here, all of a sudden if this interface goes down, now the switchover happens and the traffic now start taking this path. The SSRP VRRP was also helping us tracking this object. Okay, if this goes down, the traffic was still being sent via this. So that was in from the point of the link failovers or might be the device failovers. But what about SSO? SSO is from your control plane redundancy point of view. Okay, so if you remember those topics where we discussed the packet flow inside switch and router, so we discussed about the three planes. One is control plane, management plane, and the data plane. Agree? So this topic is about providing redundancy to the control plane. Okay, so we know that on one single switch we have couple of PSU, power supply unit, we have lot of line card, we have soup engines. Okay, so basically how does this packet flow happens in case of switch and in case of routers. Okay, so if I take back you to that presentation which was class 1 to 3, okay, from 1 1 2 and 3. So this is a packet flow within router. Okay, so these are all input traffic which hits the switching fabric, which is nothing but your data plane. All your directly connected traffic, your chef tables, uh, your MAC address table, those will be handled directly over on the data plane without even sending it to routing processor. So for routing processor, they are special kind of traffic. Let's say if the traffic was advertised or learned over on any protocol like OSPF, EIGRP, BGP. Now that cannot be handled straight away by the data plane. So that traffic, the switching fabric will push it to routing processor. Once it arrives to the routing table, routing processor, the routing table will check the entry and then it will decide that the outgoing interface has to be, let's take as an example this. Okay, now how many control plane did I interact with? Only one control plane. What if this control plane is exhausted or this control plane doesn't have any free room to process any new traffic? So your traffic will get dropped now, right? So we need some redundancy. How if I say I have two boxes, okay, and if I say this is a active control plane and this act as a redundancy control plane. Okay, now we are talking from the control plane point of view, RP point of view. This will be serving the traffic. Okay, but if this is going down, then this will take up the role. Okay, so this is achievable with the help of SSO, stateful switchover. So let me also show you the traffic flow inside switch. So this is your control plane, data plane. So whenever you have the special packet, it will be sent over to control plane via data plane. Okay, not directly. It will come to data plane. Data plane will send it to control, and then control plane will check the routing table, and then it will decide how to go out. Okay, so that was an overview about this. Now, what is the benefit of SSO? The benefit is the line card never gets reset. Okay, the line card never gets reset. What does that mean? So whatever packet we're forwarding, even though the control went down, the those forwarding interface will not go down because the secondary routing processor would have taken up the role now. So that's a benefit. So the downtime is very minor. Okay. It also provide all the network availability and the loss of the loss of sessions are being minimized due to all these benefits. Okay. Now, when do you think the SSO failover will be triggered? What are the reason for this SSO trigger? Whenever, let's say, the hardware went down. Okay. So whenever the hardware is going down, its RP, it's also going down. Okay. So we need the SSO failover happening. Whenever the clock synchronization was the clock synchronization between the two soup engine was not happening. So in that case also the SSO can trigger up. The third option would be whenever I need to do a manual SSO, okay, or might be shut down. Let's say there was some patch upgrade on my primary box. So basically I will perform a manual SSO so that I make this as active. All the traffic gets taken up here and then I can quickly reboot and shut down or upgrade, and I can just come just can make once again the SSO and bring this up and put this as backup, right? So these are some reasons, or these are some uh, triggering point. Now, whenever the SSO failover happens, keep in mind that the layer 2 traffics are not disturbed at any cost. Okay, so layer 2 are not disturbed. And in the case of layer 3, as soon as the secondary RP takes up the primary role, so the expected delay is 0 to 3 seconds. So within this 3 second, you will see the routing information table is being uh, completed in the secondary device, which is now active, and the traffic is ready to serve. Okay, so there is very less chances of downtime here. And the secondary good thing is the RIP will be cached, in the sense, let's say this is the active box, so the RIP will be getting cached, and so there will be a lot of entries already, and during the SSO this will be pushed automatically to the backup. So once the backup comes up in 0 to 3 seconds, it will already be aware of the cached list, and it knows what all hosts are connected instead of rebuilding those connections. Okay, so that's why the SSO will be benefiting in terms of less interruptions. Regarding SSO configs, what are the prerequisite to configure SSO? The first prerequisite is the two hardware must run the same version. Okay, the same version. Not that you're running one side 15.1 and other side you're running 15.2. So the SSO cannot be configured. The both RP, okay, the routing processor must run the same Cisco IOS image. This is the second prerequisite. There is one more prerequisite, that the configuration change, okay, the configuration change which is made through SNMP So the configuration change that you made through SNMP may not be automatically configured on the SNMP RP. Okay, so that means when I have two devices with RP1 and RP2, when you you might be knowing that SNMP comes with two configuration, two sets of packets. One is the monitoring and the second one is the configuration. Okay, so we are talking about the configuration SNMP. So in the case of configuration SNMP, the secondary RP may not be able to configure via SNMP. So whatever configuration we do on the active box via SNMP, not on the secondary box. The HSRP is not supported along with SSO. Okay, HSRP is not supported. The load sharing is also not supported. That's why I said one is active and second one is standby. Load balancing not supported. So what else? Okay, so I guess these are few prerequisites which you should remember. And yes, there are some prerequisites from configuration point of view. That is, the register value of these devices must be same. So you know what is register value. So when you open up your show run command or show version command, you will see something like this. Okay, so the register value of both the box should be same. And there is one more prerequisite, that is, when I have two boxes, active and standby. So when the startup synchronization happens, when the startup synchronization between active and the standby happens, okay, the configuration is not allowed. Okay, so basically if you're trying to make a configuration change, you will be prompted with an warning message that you are under SSO mode. Okay, and you're not supposed to do any configuration changes, something like your failover concepts in HA failover concept in ASA box. When you are already in a HA failover, the changes will be made up on the active box only, not on the standby, because you will get an error saying you're part of HA failover and the changes has to be done on the active box itself. Okay, so that's pretty much. And just finally, regards to the CLI command of SSO. Okay, so let's say I go to conf t, I type the command redundancy. Okay, so basically this is to enter the redundancy mode, and then I say mode SSO. So what's happening here? I'm gonna set the redundancy mode as SSO on. Okay, this is for to set the redundancy status as SSO on. Okay, so this command has to be done on both the active and the standby RP. Okay, once I do that, I can set the priority as well. I can set the priority who is my active and who the next person, whoever is standby, and then I can just come out of this mode. I can save my running configuration and I can just reboot the router. So when the routers come up, they will come up in a SSO mode. Okay, so that's about SSO, which was a small topic which was left over. It was a topic from NCore over here. Okay, so we had covered already HSRP, VRRP, GLBP. The SSO is the RP redundancies. Okay, fine. So might be next 2 days where we can complete this. Okay, 2 or 3 days. So if we keep a class tomorrow, Friday, might be on Monday we can wind up, or if we are keeping a class on Monday and Tuesday, then might be Tuesday we can wind up. Okay, so I'll let you know if we have class tomorrow or not. Might be in advance. I'll let you know. Okay, depends on the weekend classes as well. So if I have time, I would like to take a class tomorrow itself. But if not, then we will meet up on Monday and Tuesday. So let me know, guys, if you have any doubt here.
Hey, Sagar, I have a quick question about phase 1 and phase 2 of DMVPN.
Okay.
The only difference between phase 1 and phase 2 in terms of commands was that phase 2 didn't have a destination address for the spokes, correct?
Yes, we removed that command called as tunnel destination, and we added up
Mhm.
a new command with GRE multipath.
Okay.
Multipath, yes. So this was the change. We removed something and we added up
Mhm.
something.
And from phase 2 to phase 3 was on the spokes, we had the shortcut on the hub, we had the redirect
Yes,
command, but obviously it
yes,
wasn't
yes.
working.
Rest were same. Apart from the redirect on hub and the shortcut on spoke.
Okay. Thank you.
Okay, welcome. All right, guys. So let's meet up in the next class. I'll pass on the recording. Yes, the class notes are pending, which I'll create and I'll give it very shortly. Okay. So fine. So let's wind up and let's meet up in the next class. Have a nice day.